alkynes. Let's look at hydration of alkynes. We hydrate an alkyne shown here. With alkynes, it's not going to be twice the fun. You only hydrate them once. This is a hydrated alkyne. We end up in an OH on a double bond. We'll see how we get here. This is called an enol. It's a functional group. Enol. This is an alkene with an alcohol. Ene with an ol. Enol. It's also what a donkey says. Enol, or something like that. Okay? Now I'm showing mercury here. Mercury is often used when you hydrate alkynes. I will not use it in my mechanism though. It's traditionally used. It would just be analogous to like the oxymercuration, but I'm going to do it as if there's no mercury there. Just whenever you see the mercury, just do it with just the H3O+. We'll actually be hydrating an alkyne in 2 weeks in lab. It'll be a group effort, and we will not be using mercury. Of course, today mercury is sort of frowned upon, not environmentally friendly. So I'm just going to ignore this, but you'll often see it with that, with alkyne hydrations. Okay, let's just ignore that. We got H3O+. That's basically H+ and water, just like with alkenes. Pi bond can attack H+. Are we going to leave plus on left or right? Left. So this breaks away, and we end up with boom, boom, boom. I'm going to go ahead and draw it like this. We're adding a new H to the end. As this breaks away and goes bonds to the H, new H to the end, plus here. That's here. It really doesn't matter if this is down or up. That's really linear. That's SP at that point.
Why can't the water choose plus?
There you go. At this point, the water then attacks the cation. Is this really formed?
No.
Yes. That doesn't have any lone pairs to back bond. Go back to alkene. Whenever we reacted the alkene with H+, we got a cation. We didn't start back bonding until we reacted with something else. H+ cannot back bond. It's really a plus. What's the nucleophile here? We're hydrating. Water. Water adds here. What does that give? Boom, 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 boom. Double bond. There's two H's there. I'm not going to draw them now. We make the O carbon bond. Water's still there, right? Plus charge. We get to that. And then how do we get to this, which is the enol? What do we need to do? We just need to lose an H. We've done that before with afterwards. What can take the H? Well, you can use water to take it, or you can also use the minus. What's the minus here? This is very generic. There's got to be some minus. You cannot just use H3O+. It has to have a minus. What do you want the minus to be? That is what acid would work here. Sulfuric is most common, maybe phosphoric. So let's assume we use sulfuric and we got HSO4 minus here. You can show a Lewis structure. I haven't usually been doing that, but okay. But if you did, I see this on the test, and I see some of you guys do something like this. Okay, there's no HS bond in this. I'm going to draw it out. It's a standard Chem Lewis structure. Looks like this. These electrons. Take the H, these stay behind. Now you have two lone pairs, and what do we reform? Yes, reformed. This is really, we're adding water with an acid catalyst. Okay? Just like alkenes. Except we just do it once, and what do we call this structure here? Enol. It has water added to it. If you look at formula, just H2O now added, enol. Question?
Instead of using like an acid catalyst, can we just assume that it bonds, the hydrogen bonds back to hydrogen, or to water to get hydrogen?
Yes, because how does H2SO4 really exist? It's really H3O plus. So you can do it that way. I just like to reform the actual listed acid. That's the way I've always done it. So, anything different here than alkene chemistry?
No.
You're just left with a double bond there because you just only used one. We get what's called an enol. Now, before we did it again, like with HBr, but with here it does not react again. You don't hydrate again. Instead, this undergoes a rearrangement called a tautomerization. When you see things in brackets, that means it's not isolated. It's a structure that's sort of formed, but then it quickly moves on and does something else. It tautomerizes to what type of functional group? It's a ketone, right? It's the first time we made a ketone. What's the relationship between these? Well, they have the same formula. That's why I showed the formula. It's just a rearrangement. Constitutional isomers. We're going to call them tautomers. It's a specific type of constitutional isomer. We're going to call these tautomers of each other. The process of going between one or another is called tautomerization. That's a verb. These exist in equilibrium. But the ketone form, or usually called the keto form, or the carbonyl form, is your major form in equilibrium. Usually overwhelmingly. In organic 2, we'll see this again, and we'll show some where the enols may be favored. Usually ketone is favored. This is what it says in the paragraph up here. It also describes what a tautomer is. A tautomer, or the process, involves relocation of a single hydrogen and at least one pi bond. And going from here to here, we've only moved one hydrogen. We've only relocated one hydrogen. Which hydrogen did we relocate? Obviously that one. Where is it at now over here? It's now right here. Because how many H's on this carbon?
2.
How many H's there now?
1.
Now 3. Okay? So H now here. We relocated one hydrogen. Did we relocate any other hydrogens? We'll do the mechanism. Carbonyl is thermodynamically a stronger bonding arrangement. That's why it's favored. I mean, there's no H here. Oh, there's no H there. Look at it. Only one H is moved. Everything else is the same. These are called tautomers. Did we relocate at least one pi bond? Yeah, because here are the pi bonds between carbons, but now it's been relocated. You can see tautomers where more than one pi bond has been relocated. You can relocate 3 or 4. But in terms of H's, you never relocate more than one H. Okay, we've seen this. Now mercury is usually included historically. Actually in the handout that you printed out, it talks about the anniversary of when a Russian chemist discovered the hydration of alkynes. And way back when, it led to production of lots of new chemicals that could be very useful, like carbonyl compounds, ketones. So that's in the handout. Question?
Why didn't the double bond just go through another mechanism?
We're going to do that mechanism.
Okay.
Yeah, we'll do this mechanism. You need to know your tautomerization mechanism, and I think we're ready to look at it now. But do you understand the hydration to get to the enol? Pretty consistent with what we've done before. Okay, let's do this mechanism. Now first off, what conditions are we under? Because this is still the same reaction. This is all one reaction. This is still reagent. What reagents are here? That's still H2SO4. I mean, it's still H3O plus, however you want to show it. It's still acidic. Okay, we have an alkene here. Can an alkene react with H plus?
Yes.
We've done that a lot, haven't we? Well, that's the first step. Your enol has the alkene. And if this reacts with H plus, where are we going to leave carbocation? Left or right? Correct. So we have H plus here. This reacts. That means this swings down like this. So which carbon is bonding to the H? The one on the left or right?
Go on the right.
Right. Well, on the right, isn't that where we want another H added? Don't we want an H out there? Well, there we go. It's a good old-fashioned reaction with H plus. Boom, boom, boom. OH. Now there's a new H there. There's now 3. What's here?
Carbocation.
Carbocation. Okay. Now this is very analogous to what we ended with on Tuesday. What can you do here? What can we show here? What did we show last time when there was a chlorine here?
Electron pair is electron.
Resonance. These electrons can move in here, and we can show a resonance structure that looks like what? We bond to O, H there, only one lone pair, and that's a plus. There's a new H here. Did we do this with chlorine on Tuesday?
Yes.
Now, so you could be wanting to call this back bonding, but this is pi electrons. This is p orbital overlap. Empty orbital, empty orbital. And by the way, the handout I just gave you is on resonance, and we're going to start resonance in the first lecture for test 3 material. P orbital overlap here. Empty p orbital. Anytime a lone pair is next to a p orbital, lone pairs want to be in a p orbital. Okay? We're just showing the pi p orbital overlap. But look what we now have. Don't we need a double bond then?
Yes.
Let me draw that H there so it looks like this. What do we need to do to get home? Not a hydride. Hydride would mean the H and 2 electrons. If we get rid of the H and the 2 electrons, what happened to the other lone pair? Because there's 2 lone pairs there. So you don't want the H and the 2 electrons. You want to leave these 2 electrons on the oxygen. So what do we call just H? Which is proton, like acid, H plus. Basically, have we ever taken an H from an oxygen?
Yep.
This is catalyst. That means there's a minus here, and we want to reform. We started with H2SO4, we want to reform it. So this guy, take the H, leave these 2 electrons behind, we get that plus what? H2SO4 reformed. The tautomerization mechanism is catalyzed by acid. Alkane attacks H plus. Is anything new here? It's just an alkene reacting with H plus. We put the cation there, why? Because it's more substituted, but what's the more important reason we said on Tuesday? Resonance. Resonance arrow. This is an appropriate arrow. Double-headed resonance arrow. And going from here to there, how many intermediates on the board? How many intermediates in this mechanism, tautomerization mechanism? How many intermediates is going from here to there?
Oh,
One. This is your intermediate. Why am I saying that's one thing?
it's the same thing we already did.
Because resonance structures are one thing. It's like we made pink, but I don't know how to show pink, so instead I'm showing red and white. But I'm telling you, the true structure is pink. The true structure is just one thing, okay? You have to learn more about resonance structures. Hopefully you've been doing some reading. We'll be doing that soon. Only one intermediate here. Okay, there's your tautomerization mechanism under acidic conditions. All right, there's a way to remember that. It's called Oreo. I don't know who made that up. I think it was me. I'll look it up on the wiki. What does Oreo stand for? What did we do here? First thing we did was we put a proton on. Okay, H plus on. Isn't that what we did first? H plus on. Where did we put it at? Where we wanted it. Don't we want a new H there? Put it where we wanted. But it worked out that way. H plus on, that's your O. Then what did we show on the board? Resonance, that's your, we got an O, then we got a Re. What did we do over here? We took it off. H plus off. There's your other O. Oreo. Okay, that's how you remember tautomerization mechanism. It's good, right? Okay. Does it work with this tautomerization? Yes. Does it work with the tautomerization that we're going to do in Organic 2 in March? Yes, absolutely. It works with all tautomerization mechanisms. Okay? What does it stand for? On, resonance, off. Under acidic conditions, if you're doing basic conditions, you reverse the on and off. Under basic conditions, it would be off, resonance, on. We may do a basic. Tautomerization can be catalyzed by either acid or base. So all that happens, and basically you take that alkyne, you heat it with aqueous acid. What are you going to get? You're going to get this ketone. Where the alkyne has been hydrated. Because if you look at formula, this formula has H2O compared to the starting formula, but it's in the form of a ketone. Let's look at more tautomers. The keto form, the enol form, very important. We'll see it again in Organic 2. There's Oreo. Not in any textbooks yet. Still working on that one. Recognizing tautomers. Which of the following are enol forms of the compound in the box? Now, apparently these are the same, so just don't worry about this. Which of these are enol forms of the compound in the box?
First two.
What are we looking for? We're looking for a structure where only one H has been relocated, and then pi bonds. Which ones fit that?
First two.
Yeah, it's the first two. Not that one. Goes over here. Compared to this, I got an H relocated, because obviously that there ain't no H there. I can't see the structure there. I mean, there's two here. But there's only one there. But there's also two here. There's only one here. And there's one here, but there ain't none there. I mean, I can't count them up. It's like 3 or 4 have been relocated. That's not a tautomer. But these two are, because basically there's one. Over there you got 2 H's here, but now you only have one there and the other one is here. Basically, what do you call the tautomer of a ketone? Enol. That's the tautomer of a ketone. And what's an enol? It's an alkene with an OH on the alkene. I mean, is that an enol? That's not an enol. The OH is not on the alkene. So that's a good clue that it's not the tautomer also. First two are tautomers. You can have a double bond on either side. So recognizing tautomers. How about below? Are these tautomers?
Yes.
No.
Yes. Yes.
Yes.
Are these tautomers of each other?
Yes.
What H has been moved? Obviously the nitrogen has only one H here. It's been moved where?
Into the ring.
Where's one of these H's at now? It's right here. Okay, it's right there. No other atoms have moved. Just that one H has been relocated. You can look. I mean, there's no H's there. There's no H's here. That's it. But other than the H being moved, what else has happened? Pi bonds have relocated. How many have relocated? 2 pi bonds in this case. Okay. Those are tautomers. Now that's not like carbonyl tautomers. That's more complex, but those are called tautomers. Question?
So it doesn't matter how many pi bonds move, it can still be a tautomer.
Doesn't matter how many pi bonds. It could be 20 pi bonds, but only one H. If you move 2 H's, not tautomer. Okay, let's try this reaction with BH3. If you do BH3, you're also going to do a hydration, but we're going to get a little bit different outcome, right? That's going to give the enol with the OH on the other because, I'll pull this down, where do we want to leave cation if we think about that? Left or right? On the left. So this attacks BH3. So we add the BH3, that's a minus there, and that's a cation. I really need to draw these out, right? And that the cation we form, but is it really formed? No, doesn't this do a hydride shift, and don't we then get BH2? There's a new H here, right? And by the way, if we show this, aren't these on the same side in terms of like EZ? Because they comes in from the same side. That's not ultimately going to matter. What does the magic step do? Place this with an OH, and when you do that, what do we get? We get that. So it's the same chemistry as with alkenes. I mean, I just got the H drawn. But what do enols do? They tautomerize to what form? Carbonyl form, not always a ketone. It is always a carbonyl. And in this case, it's going to be an aldehyde. Because ultimately, the pi bond ends up between the oxygen and carbon, and the H ends up here. Now, don't let this confuse you, because I like to just draw it in. That H is still there. Okay? That H is that H. There's only one, but now there's 2.
Is it different because you don't have an acid?
Do what?
Is it different because you don't have an acid?
What conditions are we under here? Basic or acidic? Basic. Since it's basic, let's do a mechanism with basic. That is, we have hydroxide. Not H+, but hydroxide. And we haven't done something like this, but it's sort of straightforward acid-base chemistry. And if we keep in mind Oreo, what do we need to do first? Here, it's O stands for off. What H do you want to take off? The one that needs to come off. Which one needs to come off? The one on the oxygen. The base takes that H, leaves the electrons behind, standard acid-base chemistry. So we get minus here, plus what? Plus water. Acid-base chemistry, I gave you that mechanism handout. Okay. And what do we call that? Off? What do we do next? Resonance. Now see here, we haven't really done this type of resonance. With resonance, we're going to take these electrons and move them in here. And we're going to push these out. We'll do more of this next week and the week after. But once I show you the arrow, what is this arrow doing? Making pi bond. What is this doing? Pi electrons are moving out onto that carbon as a lone pair. So we now have a lone pair there. That's it. But we have to have the same, that's a minus. Minus is now there. What do we need to do to get home? Put H on. Where do you want to put it on at? Where it needs to go? What's going to supply the H? Water. These electrons take the H from water. These electrons move on to oxygen. That gives this. Okay, that H is there. I just don't have it drawn in here. Now we have two H's there. And what do we reform? Over here. Hydroxide was our catalyst. Okay? Catalyst reform. Oreo, off, resonance on. So that's the reverse. So on, resonance off. That one's a little less intuitive because we haven't done sort of base mechanisms. We haven't done resonance like this, I don't think. Okay. We do need to move ahead, guys, but we need to finish up this today. Reduction of alkynes. Reduction of alkynes is going to be, well, we got to do reduction of alkynes, and then we're going to do sort of a miscellaneous acid-base chemistry. Chapter 10.5. Let's see. Test on Tuesday. Anybody object to moving it to Thursday? What? We do like a motion and vote? Let's finish up Okay, reduction. Reduction, we can do hydrogenation, hydrogen, have an alkyne, precious metal catalyst like platinum or nickel or something. Basically, we add two H's. Okay? How do we add H's from a metal catalyst like this? Syn or anti? Syn. And so this is where they're added to the same side. You're going to get, after you add two H's, one equivalent of hydrogen gas, you're going to get a cis alkene. Because the two H's are on the same side, pushing the existing groups one way towards the other side. Now, under regular conditions, it doesn't stop here because we know that alkenes can be hydrogenated. And if you add two more H's, what do you get? Well, now you're just down to the alkane. Now you have two new H's here, and now there's no stereochemistry. Just free rotation. You don't even have sister trans. And so if you just do this with H2 and say two equivalents, or like excess, and then your favorite catalyst, such maybe nickel, you'll go all the way to the alkane. That would be a hydrogenation. Also called a reduction, because when you add H's, it's called a reduction. Pretty straightforward. And you typically can't stop here with a precious metal catalyst. You can't stop there. And you have to use two equivalents or excess hydrogen. It is hard. That's another reason it's hard to stop there, because it's hard to measure out a gas. I mean, it could be done. It's just not very convenient. What if you wanted to stop at the cis alkene? Well, chemists have figured out a way to do it. Turns out if you use what's called a poison catalyst, it'll stop at the alkene, the cis alkene. A poison catalyst is a catalyst where something has been added to it to make it less reactive, and it has become poisoned.
That's the same thing as doping.
Yes, yes. Doping. Examples, like palladium, if you add barium sulfate to it or lead sulfate, it'll make it less reactive as a catalyst. And then it turns out that you can, if you use that catalyst, you can stop at the cis alkene. You may see poison catalysts listed like with barium sulfate or lead sulfate. Lindlar's catalyst, which is actually, it may contain lead, I'm not quite sure. A lot of times you'll just see it said Lindlar's catalyst. So whenever you see Lindlar's, just know it's a poison catalyst. And in this particular case, it'll stop at the cis. It'll either say poison or Lindlar's. Do you know that Lindlar's is a type of poison catalyst? There's a lot of things that can be added when you get to the advanced level. But it'll probably typically say poison. Is there a question over here?
Why does the two hydrogens always add 6 again?
Well, it's just like when we did alkenes. The hydrogens come from the metal surface, and it's like they shoot in as darts. It's that sort of metal mechanism. We really didn't look at the mechanism, but we said that it comes from the metal syn addition. Okay. So we now know how to get cis alkenes from alkynes. How do you do that? Hydrogenate using a poison catalyst. We'll stop. What about transalkenes? Well, hydrogen doesn't do trans because if they come in the same side, you'll get cis. Well, we can show how you get trans, so we can have a complementary reaction. You can get transalkenes from an alkyne by doing a dissolving metal reduction using sodium and ammonia. And this is going to be our first look at a radical reaction. And it will give trans products. Partial reduction, okay? Still partial reduction or incomplete reduction would be trans. This is sodium metal, oxidation state of 0, ammonia. Minus 33 because it's done in ammonia as a solvent. Ammonia is usually a gas, but if you cool it to minus 33, it'll become a liquid, and you can use it as a solvent. So that's the cold temperature. What you do is you condense your ammonia down, you get it cold, and it becomes liquid. Then you cut your sodium and put in there. When you add the sodium, it becomes really bright blue. The color of these two blue shirts right here. Deep royal blue. Okay. I've never seen it in real life, but I've seen videos. Real deep blue. What is that? It's called put this into ammonia. You get, what does sodium like to do? It likes to become what? Plus or minus? So it likes to give up what? It likes to give up one electron. It'll give that up in a lot of redox processes.
What is the circle above it?
What is the what?
The circle above it?
It's usually how you show like a metal oxidation state of 0. As opposed to you saying, is this an ion?
Okay.
I'm clarifying that this is sodium metal with oxidation state of 0. Sodium will give up an electron to the ammonia solvent, but it's known to be sort of like free electrons. I'm just showing an electron here. And the ammonia sort of just solvates it. Okay, solvated electrons. Now, since the sodium gave up an electron, you got this. We also have sodium, but now it can be shown like what? Now that's +1. Okay. Now this is a little bit like, well, what's going on here? Where's the electron? Well, you can look it up. Okay, you can find the video. It's called Solvated Electrons. It's an amazing thing. Why does it turn brilliant blue? I'm not sure I can tell you. It's amazing chemistry and amazing, Mother Nature doing something here. These electrons can be, if we put something else in here that will accept the electron, we can then do a reaction. Well, this will accept the electron. Now, usually we've been attacking something. Here, we're going to add something to this. This is a single electron. I can draw it with an E or I can make a dot. Okay? I'll start with an E. Once we get it up there, we'll do dots. One electron, this is symmetrical. Doesn't matter which carbon of the alkyne, the electron moves in. Whenever you move one electron, you use a fishhook arrow. Okay? That's a regular arrow, that's a fishhook arrow. Regular arrow is 2 electrons, like a lone pair or a bonding pair. It's just 1 electron. One electron gets pumped in. These electrons move over here, so that's 2. Those 2 move over here. What does that give? We now have a carbon with a single electron. What does this arrow mean to us? These electrons moving onto carbon as what? Lone pair. Now at this point, this carbon will be like this. Now, really, I'm going to draw these like that. It really didn't matter. But right here is where you get your trans. Because it really has an option. This has an option here. The trans is preferred. That makes sense. I mean, these groups being sort of anti is preferred. What's the charge of an electron? -1. If we add a negative to a neutral, what should this charge of this be? Negative. Where's the negative? Right here. That carbon owns 1, 2, 3, 4, 5. It's only supposed to own 4. What's the charge of this carbon? It owns 1, 2, 3, 4.
0.
That's neutral. An electron pumped in and it led to this anion. Carbanion. What do we need to add to each carbon? H's. Next step is this will take an H. What can supply the H? There's only one thing that can supply it. NH3. These electrons will do what? Take an H. These electrons will do what? Stay behind. So what do we now have bonded here? H. Still a radical here. It's the first time I've used that. What do we call something with an unpaired electron? Radical. It's a radical. What did we make here? In H2 with 2 lone pairs, that's a minus. The next step is for another electron to pump in here and team up with that one. And this gives now 2 electrons, but that's now minus. Where did the other electron come from? Well, we didn't balance this reaction, but if you balance it, you need 2 sodiums. You also need 2 ammonias. We'll show the byproducts up there. So 1 electron from a sodium comes in, and then another sodium supplies an electron. It comes in. What do we need to do to get home? We've used 1 ammonia. What's the second ammonia for? You need to take another H. These electrons take another H. Let's take an I. What does that give? It gives that. And what did we form? We formed another NH2 minus. So there you go. You pump in single electrons, you eventually get anions. The anions take H from ammonia. Why is it trans? Right here it has an option and trans is preferred. Why don't you get trans with dehydrogenation? Because you don't have the option. Because the H's come in from the same side. Boom, there was no option. So what is the byproducts? This reacts with 2 of these to give that plus what? Well, what do we form up there? 2 NaNH2s. This is ionic, right? This is 2 sodium ions. Sodium ion was formed when the first electron was given up. Sodium ion was formed when the second electron was given up. How did we get the 2 NH2 minuses? We formed one here when it supplied the H, and then we formed another here when it supplied the H. Every minus has a plus with it. I mean, here you go. That's ionic. Just like sodium chloride, it's sodium minus. 2 of those, that should be balanced now. 2 of these H's end up here. Let's first look at a radical reaction. Fish-hook arrow. This is the first time we added something to the alkene as opposed to the alkene attacking an electrophile. So really, the alkene here is called the electrophile. It loves these electrons. It's the first time we've seen the pi bond be an electrophile. Questions about that mechanism?
So is the only thing that the Na does just supply that extra electron?
It supplies the electron twice.
Yes,
You got to have 2 equivalents of sodium.
Okay.
Yeah.
And then to kind of like count the NAs. So yeah, at the end is 2 Na and NH2. So we can like say since we use 2 electrons, we know there's 3 NAs.
2 NAs?
So we use 2 electrons to the mechanism.
Each sodium gives up 1, so you need 2 sodiums.
Correct.
And both the sodiums become sodium plus.
And they're
So that's why I drew up there. 2 sodium pluses and 2 NH2 minuses. I have a feeling that some of you don't know that this is an A plus. If I drew NaCl on the board, isn't this an A plus Cl minus?
Yeah.
Well, that's an A plus NH2 minus. I mean, just because you draw this formula doesn't mean it's not ionic. We form 2 sodium ions and we form 2 NH2 minuses. Because each time the ammonia gives up an H, you get an NH2 minus. Okay, so take a look at that. Why is it called dissolving metal? Because typically metals are not soluble. But once this reaction takes place, the sodium actually dissolves because it becomes, that ionic sodium NH2 is going to dissolve, be dissolved. At the end of the reaction, your metal is dissolved. And anytime you do a reaction where the metal dissolves, we can call it what? A dissolving metal reaction. Some of these things are not rocket science, they're just terms, right? Okay, the last thing we're going to look at with alkynes is something we saw back with acid-base chemistry. That's the acidity of terminal alkynes. H of a terminal alkyne has some acidity, enough that we can do some chemistry with it. And we can deprotonate it. What's the pKa of a terminal alkyne? About 25. It should be on the list in your lab manual. What type of base is needed to deprotonate that? How acidic is something with pK of 25?
Not there.
Not very. But it's acidic enough to do something. A couple of the types of bases that are commonly used. N-butyl lithium. You may not have said that before. N-butyl, which is that. Lithium is plus. It's just a carbanion on the end there. That's called N-butyl lithium. Normal meaning just straight chain. And then the lithium is plus. But these electrons will take the H, leave these behind. What do you get? When you leave that behind, what do we now have there? Lone pair? That's now a minus. Carbanion. It's a carbanion. Carbon with an anion. Sometimes call it acetylide anion because the simplest alkyne is called acetylene. And then the lithium plus will sit with that. But what do we make here when this took on an H? Just butane. Now butane has a pKa of greater than 40. So in terms of this equilibrium, which is favored, 25 or 40? 40. By how much? By 10 to the 15 at least. So it's favored by what? 100 gazillion. Okay? So is N-butyl lithium strong enough to deprotonate that? Yeah. 100 gazillion is a good equilibrium. Okay? The equilibrium looks like this. Okay? Even smaller. It's pretty much done. It's all the way. Another base that can be used is NaNH2. Where have we seen that at?
Last reaction.
We just made that as a product in the last reaction. This is called sodomid. Sodomid. That's kind of slang. Sodium. The anion of an sp3 nitrogen is called an amide. That's a terrible name because amide means something else to us. An amide has a carbonyl. Nitrogen anions, for some reason, are also called amides. Just forget about it. Don't worry. That's why that's called sodium amide sodomid. All right? Slang name, look it up. In practice, it's a terrible base because it's not soluble in organic solvents. It's so ionic. You can't put it in water or you won't have it won't exist in water. But it's very common textbook. Okay? Well, it's ionic. You have NH2 minus. These electrons take the H, stay behind, you get that plus what? Ammonia. Ammonia has a pKa of 35 as an acid. 25, 35, which side's favored? 35, by 10 to the 10. So it's favored by what? 10 billion. 10 billion to 1. That's pretty much complete, right? Way that way. Both of those bases will deprotonate and make your sort of acetylide anions, or your alkyne carbanions. Will sodium hydroxide do it? Well, apparently not. Big X there. But let's see. Let's look at our pKa's and see why. So hydroxide takes that, leave that behind, you get this plus water. This is 25, what's water? 16, which side's favored? 25. Weaker acid's favored. That's the weaker acid. This side's favored, right? So the question is sodium hydroxide strong enough to deprotonate this and take you over there?
No.
No. I mean, this is the favored side. Whatever we say is something good to do that, not if that side's not favored. This is the favored side. The take-home is sodium hydroxide is not strong enough to do this, but those stronger bases are. So which side, if this equilibrium here, show the equilibrium. Which side's favored? Be this, right? This side's favored. What does that mean in terms if you take this and put it in water? Will these react to do anything? They will go over here. That is, if you put your carbanion in water, it's no longer going to be a carbanion, you're going to protonate it. So that's the reverse. The reverse is favored. That takes us to the very end, a nice little application of that reverse right there. Back in the 1800s, coal miners used to wear little helmets where they had a fire up here. It would be like a flashlight, back before batteries were common. And they'd have a little fire, and then they could see where they were going. What would they do? They would have a little helmet with a little apparatus up here with calcium carbide. What is calcium carbide? CaC2. That's where the C2 is. That's your C2. So that's two minuses, and you got a calcium 2 plus to go with it to balance it. Calcium carbide. It's an ore, or it could be. I don't know how they find it or how they make it, but it was available back then. So what they do is they have a little calcium carbide component, and then they would drip water on it. See, that looks like the anions, right? You got two of them. What happens when this comes into contact with water? You put the H on, right? That's what we did above. This will put the H on. And when you put the H on, what do you get? Put the H on each end. What is this? Acetylene. It's two carbons. It's acetylene. And what does acetylene do? It will burn, like acetylene torch. The take home is, if you somehow they dripped water on it and they lit it, and it would burn. It would burn. Sounds a little dangerous. Right? Somehow they controlled the drip, and then they would light it, and this would produce. This is going backwards. It's like this going backwards. You got to look at it. Produce acetylene, and you light it, and it will continuously produce it, and you get calcium hydroxide. You can also have canister lights that did this, but I think they put it on their helmet. And then light it up. And they could work with their hands and stuff. Okay, during test 3, we will make these carbanions on the acetylide or the alkynes, and we will do chemistry with them. Here we just showed that it can be done, what bases you use, etc. Now in 3 weeks when we do this, I'm going to say, remember when we used lithium to deprotonate? And you're going to say, okay. So the test is bad situation to be in.
There's no reason to move it.